Tantor Audio, a division of Recorded Books, presents The Ethical Algorithm, The Science of Socially Aware Algorithm Design by Michael Kearns and Aaron Roth. Narrated by Teri Schnaubelt. Publisher's Note: this audiobook includes bonus material. Please visit Tantor.com and type Ethical Algorithm into the search box. Follow the link to the book's page. Then, under the Supplemental Content section, please enter the access code GATHER, and then click the Unlock button to access the bonus material. The code should be entered in all lowercase letters. All figures and tables referenced in this audiobook can be found in the bonus material. Introduction. Algorithmic Anxiety. We are allegedly living in a golden age of data. For practically any question about people or society that you might be curious about, there are colossal datasets that can be mined and analyzed to provide answers with statistical certainty. How do the behaviors of your friends influence what you watch on TV or how you vote? These questions can be answered with Facebook data, which records the social network activity of billions of people worldwide. Are people who exercise frequently less likely to habitually check their email? For anyone who uses an Apple Watch or an Android phone together with the Google Fit app, the data can tell us. And if you are a retailer who wants to better target your products to your customers by knowing where and how they spend their days and nights, there are dozens of companies vying to sell you this data. Which all brings us to a conundrum. The insights we can get from this unprecedented access to data can be a great thing. We can get new understanding about how our society works and improve public health, municipal services, and consumer products. But as individuals, we aren't just the recipients of the fruits of this data analysis. We are the data, and it is being used to make decisions about us, sometimes very consequential decisions. In December 2018, the New York Times obtained a commercial dataset containing location information collected from phone apps, whose nominal purpose is to provide mundane things like weather reports and restaurant recommendations. Such datasets contain precise locations for hundreds of millions of individuals, each updated hundreds or even thousands of times a day. Commercial buyers of such data will generally be interested in aggregate information. For example, a hedge fund might be interested in tracking the number of people who shop at a particular chain of retail outlets in order to predict quarterly revenues. But the data is recorded by individual phones. It is superficially anonymous, without names attached, but there is only so much anonymity you can promise when recording a person's every move. For example, from this data, the New York Times was able to identify a 46-year-old math teacher named Lisa Magrin. She was the only person who made the daily commute with her home in upstate New York to the middle school where she works, 14 miles away. And once someone's identity is uncovered in this way, it's possible to learn a lot more about them. The Times followed Lisa's data trail to Weight Watchers, to a dermatologist's office, and to her ex-boyfriend's home. She found this disturbing and told the Times why. It's the thought of people finding out those intimate details that you don't want people to know. Just a couple of decades ago, this level of intrusive surveillance would have required a private investigator or a government agency. Now, it is simply the byproduct of widely available commercial datasets. Clearly, we have entered a brave new world. And it's not only privacy that has become a concern as data gathering and analysis proliferate, because algorithms, those little bits of machine code that increasingly mediate our behavior via our phones and the internet, aren't simply analyzing the data that we generate with our every move. They are also being used to actively make decisions that affect our lives. When you apply for a credit card, your application may never be examined by a human being. Instead, an algorithm pulling in data about you, and perhaps also about people like you, from many different sources might automatically approve or deny your request. Though there are benefits to knowing instantaneously whether your request is approved, rather than waiting 5 to 10 business days, this should give us a moment of pause. In many states, algorithms based on what is called machine learning are also used to inform bail, parole, and criminal sentencing decisions. Algorithms are used to deploy police officers across cities. They are being used to make decisions in all sorts of domains that have direct and real impact on people's lives. All this raises questions not only of privacy, but also of fairness, as well as a variety of other basic social values, including safety, transparency, accountability, and even morality. So if we are going to continue to generate and use huge datasets to automate important decisions, a trend whose reversal seems about as plausible as our returning to an agrarian society, we have to think seriously about some weighty topics. These include limits on the use of data and algorithms and the corresponding laws, regulations, and organizations that would determine and enforce those limits. But we must also think seriously about addressing the concerns scientifically about what it might mean to encode ethical principles directly into the design of the algorithms that are increasingly woven into our daily lives. This book is about that emerging science of ethical algorithm design, which tries to do exactly that. Sorting through algorithms. But first, what is an algorithm anyway? At its most fundamental level, an algorithm is nothing more than a very precisely specified series of instructions for performing some concrete task. The simplest algorithms, the ones we teach to our first-year computer science students, do very basic but often important things, such as sorting a list of numbers from smallest to largest. Imagine you are confronted with a row of 1 billion note cards, each of which has an arbitrary number written on it. Your goal is to rearrange the note cards so that the numbers are in ascending order, or more precisely, to specify an algorithm for doing so. This means that each step of the process you describe must be unambiguous, and that process must always terminate with the note cards arranged in ascending order, regardless of the numbers and their initial arrangement. Here is one way to start. Scan through the initial arrangement from left to right to find the smallest of the numbers. You're allowed to use a pencil and paper as storage or memory to help you, which perhaps is written on the 65,704th note card. Then swap that note card with the leftmost note card. Now, the smallest number comes first in the list, as desired. Next, rescan the cards, starting second from left to find the second smallest number, and swap its note card with the second from left. Continue in this fashion until you've completely sorted the list. This is an algorithm. It's precisely specified, and it always works. It's also a bad algorithm, in the sense that there are considerably faster algorithms for the same problem. If we think about it for a moment, we see that this algorithm will scan through the list of 1 billion numbers 1 billion times. First from leftmost to rightmost, then from second from left to rightmost, then from third from left to rightmost, and so on, each time placing just one more number in its proper position. In the language of algorithms, this would be called a quadratic time algorithm, because if the length of the list is n, the number of steps or running time required by the algorithm would be proportional to the square of n. And if n is in the billions, as it would be, for example, if we wanted to sort Facebook users by their monthly usage time, it would be infeasibly slow for even the fastest computers. Fortunately for Facebook, and the rest of us, there are algorithms whose running time is much closer to n than to its square. Such algorithms are fast enough for even the largest real-world sorting problems. One of the interesting aspects of algorithm design is that even for fundamental problems such as sorting, there can be multiple alternative algorithms with different strengths and weaknesses, depending on what our concerns are. For example, the extensive Wikipedia page on sorting lists 43 different algorithms, with names like quicksort, heap sort, bubble sort, and pigeonhole sort. Some are faster when we can assume the initial list is in a random order, as opposed to being in reverse sorted order, for example. Some require less memory than others at the expense of being slower. Some excel when we can assume that each number in the list is unique, as with social.
Sample complete. Ready to continue?